Today is an introduction of alkane nomenclature, and alkanes are some of the simplest organic molecules that we typically see, and a good place to start because the nomenclature or the naming rules that we learn for alkanes are going to apply as kind of the background nomenclature rules for more interesting compounds. In other words, you're going to take what you learn about naming alkanes and start with that with future compounds and then add in the additional things. So for example, this right here is an alkane because all of the carbons are sp3 hybridized and there are no double or triple bonds. And there's no other atoms besides carbons and hydrogens. This is an alkene. An alkene has that double bond. So again, an alkane is a very simple compound. The two elements that comprise alkanes are carbons and hydrogens. The hybridization of all of the carbon atoms in alkanes needs to be sp3. And the types of double bonds that we deal with are just single bonds across the board. So we'll just that's kind of a basic introduction into alkanes. You look for all carbons, hydrogens, so this not an alkane because that's not a carbon or hydrogen. You want all of the hybridization to be sp3. Well, that's sp, that's sp, that's sp2, that's sp2. These are all sp2, so these don't meet that second criteria. And then we need single bonds across the board. So that one's out, and that one's out, and that one's out. So this is how you can look at a compound very quickly and identify it as an alkane. And even when we call something not an alkane, notice how it still has some pieces of it that are alkanes. So for example, in this has a triple bond. So this is called an alkyne. This portion of the molecule over here meets all three of these criteria. So this technically has both alkane and alkyne in it. But because alkanes tend to be so boring, if the only time we really refer to these as alkanes is when that's all there is. If there's anything else, then we kind of ignore the alkane and start focusing on the more important functional groups. So now we're ready to define this. So providing a descriptive explanation for alkanes, these are simple organic molecules that contain only carbon and hydrogen. All carbon are sp3 hybridized and no pi bonds. That means no double or triple bonds. Alkanes are predictable. And what I mean by that is if you know the number of carbons in the alkane, it is easy to predict the number of hydrogens in that alkane. And this is true for both linear and cyclic alkanes. We'll deal with these cyclic or cycloalkanes later on, but let's just talk about linear alkanes. And for linear alkanes, these are ones that don't have any rings inside of them. If you know the number of carbons, you can mathematically determine the number of hydrogens. And the reason for that is that the number of hydrogens is equal to 2 times the number of carbons plus 2. So if you have 1 carbon, then 2 times 1 plus 2 is 4. If you have 3 carbons, then 2 times 3 plus 2 is 8. If you have 4 carbons, then 2 times 4 plus 2 is 10. If you have 5 carbons, 2 times 5 plus 2 is 12. And if you have 6 carbons, 2 times 6 plus 2 is 14. This is kind of a background piece of information that we keep coming back to. For now, the nice part about this is if you see a molecular formula, for example, a C7, and there are 16 hydrogens, then because 2 times 7 plus 2 is 16, you can say that while I don't know exactly how those carbons are connected, I do know that this is a linear alkane. If you have anything less than 16 hydrogens, then you have an alkene or an alkyne or a ring in the system. There's something interesting going on. Linear alkanes can be straight or branched. So a cyclic alkane is one that has a ring system, and a linear alkane, like butane right here, just means that it doesn't have any rings. It does not mean that it doesn't have any branches. So both of these are referred to as linear alkanes. This one just happens to have a branch in it. The chemical formula for butane is C4H10. Here's the carbon skeleton diagram, and here's the Lewis structure, and you can count 4 carbons and 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And now, what is the chemical formula for isobutane? Well, based on the carbon skeleton diagram, it has 1, 2, 3, 4 carbons. And because it's a linear alkane, 2 times the number of carbons, 4, plus 2 tells me that it should have 10 hydrogens. And when I check the structure, the Lewis structure of isobutane, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total hydrogens. So both butane and isobutane have a chemical formula of C4H10. Compounds with the same chemical formula but different arrangements of bonds are called constitutional isomers. In fact, that was one of the definitions that you needed at the beginning. So we'll just copy and paste that here. Constitutional isomers, compounds with the same formula but different arrangement of bonds. So now, are there any other constitutional isomers for C4H10? In other words, can I take this carbon off right here? Can I break it off and attach it somewhere else besides that middle carbon and get a different molecule? And the short answer is no. The long answer is you could try breaking this carbon here off the end and moving it to the other end, and all you would end up doing is reproducing butane. So there's really no other way of trying to arrange 4 carbons without having any rings in the system, and these are the only 2 constitutional isomers that exist for C4H10. We're going to look at some bigger carbon chunks like C5s, C6s, and think about how many different constitutional isomers we can get with more carbons. But before we do that, it is better to come up with some names for these different carbons. And the names are methylene, methyl, and methine. And here I have, this is 1, 2, 3, 4, 5. There's 5 total carbons. So this is pentane. And they used to have a really old-fashioned nomenclature system where they would call the straight chain normal pentane. And that was part of the official name, normal pentane. And then that got too tedious, so they just started calling it N-pentane. And you'll still see that from time to time. It's kind of an outdated system of nomenclature. But because there are different ways of arranging 5 carbons, it is helpful to use that outdated system of nomenclature to specify that this particular pentane is a straight line, so they call it N-pentane. I think they probably should have called it linear pentane, but that would be too easy. Okay, so any carbon that has 3 hydrogens connected to it is called a methyl group, and a carbon with 2 hydrogens is called a methylene group. You can have a carbon with 1 hydrogen, and this particular compound doesn't have any, but if you have a carbon with 1 hydrogen, it's called a methine group. If we go back up to isobutane, in the Lewis structure, you can see the methine carbon right there. So isobutane has 3 methyl carbons and 1 methine carbon. And this now allows us to fill in the last of the definitions. A methyl group, oops, put my cursor down here. A methyl group is a CH3, a methylene is a CH2, and a methine is a CH, respectively. So now that we have the right nomenclature for methyl, methylene, and methine carbons, let's come up with the different constitutional isomers of pentane. In other words, how many different ways are there of arranging a 5-carbon compound without pi bonds or cyclic systems? And the short answer is 3. And here are the 3 different constitutional isomers of C5H10, and they have what are called common names. We're going to learn later on what the systematic names are, but pentane, isopentane, and neopentane. And then the question asks us to identify the methyl, the methylene, and the methine carbons. So I'm going to go ahead and just, let's see, we're going to put a circle around any of the methyl carbons. So there's a methyl group and a methyl group. I'll make these these circles a little smaller and aim a little better. There we go. The isopentane has a methyl group here. Whoops. And a methyl group right there. And then another one right there. And your neopentane is going to have four methyl groups. There'll be one right here, one right here, notice this carbon in the middle right there doesn't have any hydrogens connected to it. It can't. It's already got 4 bonds. There's no room to put a hydrogen, and it doesn't have really a special name. Sometimes we refer to this as a quaternary carbon, and we'll talk about primary, secondary, tertiary, and quaternary carbons later on, but it doesn't have a name like methyl, methylene, or methine. So we've labeled all my methyl groups right here. I'm going to put a different shape. I'll just put a box around the methine carbon. Now this is the one that's connected to one hydrogen. And then we'll put, let's see, I'll put an oval, I guess. That's going to not work. Let's use a solid box, and we'll drop that here on the methylene carbons. So there's a methylene. Methylene, remember, is CH2. And so then I'll just make a figure legend for this so that you can figure out what I'm trying to do. That's not the right one. And then we had circles. And so the solid box was equal to the methylene groups. The dashed box was the methine, and the circle was the methyl. There we go. Okay, so we have all the constitutional isomers of pentane, and we've labeled the methyl, the methylene, and the methine groups. These common names for pentane are common names that you should be familiar with as the semester progresses. So it's useful to know these ones. I actually have them written down here. So below are shown all the linear alkanes of 5 carbons and less, and their name. And I have actually the answer to these questions up here already. So we've already looked at butane and isobutane. There's that normal butane, which is entirely optional. And then we have the normal pentane, which, again, equally correct just to refer to the normal pentane as pentane. You have isopentane and neopentane. And if you'll notice that as you continue to add carbons, then you continue to find more and more ways to arrange those. So the constitutional isomers start to go up. And there's not really a mathematical relationship that I've noticed that allows you to predict how many constitutional isomers you'll get based on the number of carbons. Now we want to draw the constitutional isomers of C6 H14. 6 carbons is a hexane, so there are going to be 5 different constitutional isomers, the family of hexanes. So let's start coming up with what those might look like. The simplest one would be a straight chain. So the 2 right there. So we have 6 carbons right there. And this one would just be your regular hexane. Then we're going to take one of the carbons off of the end and put it there. So it would be a 5 carbon group with 1 carbon breaking off of the edge. You could also take that methyl group that we popped off the end, and instead of putting it a position in, you can put it right in the middle. So these 2 compounds right here are constitutional isomers of each other. And again, the way you check that is, in order to get from this compound to this compound, what would I need to do? And the answer is I would need to break that methyl group off and reattach it somewhere else. Anytime you are breaking a bond, sigma bond, and reattaching it elsewhere, that's the definition of a constitutional isomer. So there's 3 of the 5. Then what I'll try to do is break the carbon off of the other end of this and move it to that position, so we can do something that looks like this. So we have a 4-carbon chain, and then I break one of the carbons off of the end and put it there. Or we could take that 4-carbon chain and put 2 carbons, 2 methyl groups on the same position. I'll go ahead and just auto-name all of these ones, and we'll talk about how we name these things later on. The purpose of checking the names is that's usually the easiest way to tell that we're not dealing with the same compound. And so if I take this compound and bend it like this, it's still the same name. It didn't fundamentally change the compound. So you can take these bonds and move them all you want. And so one of the problems that you come up with when you're trying to come up with a large list of different constitutional isomers is you'll actually end up making the same compound 2 or 3 times. So I really hate these types of questions because it's easy to come up with a lot more possible constitutional isomers just because you didn't realize that you kept making the same compound over and over again. For example, if you had tried to do this compound but oriented it differently, you might convince yourself that these are 2 different compounds, and they're not. And if you check the name on them, the name of the compound will tell you that these are actually the same compound. So here are the 5. Here are the 5 constitutional isomers of hexane. The purpose of this was to get you used to the idea that you can take the same number of carbons and arrange them in a variety of different ways and produce what are called constitutional isomers. Hopefully you also noticed that we no longer used what are called common names. So notice how for the 3 constitutional isomers of pentane, all 3 of those names it said pentane and then it had some type of prefix. When you look at these compounds, you'll notice, well, here's the hexane, and when I moved that carbon off the end to a different position, I now didn't call it some type of hexane, it became some type of methylpentane. And the reason for this is these names right here are common names, and there's not really a good rule system for knowing them. You just have to memorize them. And they realized, hopefully fairly quickly, that having people memorize a family of names for each of the possible constitutional isomers can be pretty tedious. So instead, we're going to come up with a system of naming these that allows you to apply some set rules and be able to name the compounds based on those rules. And that's exactly how these different names are generated. So let's talk about those rules for nomenclature. Nomenclature is, I guess, the art or study of naming things. And now we need to learn how to name simple alkanes. So the first step is to determine the parent chain. The parent chain is kind of your point of reference, and it is the longest continuous stretch of carbons. So for this compound, there are a total of 1, 2, 3, 4, 5, 6. There are 6 total carbons, but the longest continuous stretch of carbons that you can find is 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. And either one of those 5s could be your parent chain. And in this particular case, it's going to give you the same name no matter how you do it. So it tells me to circle these. I'm going to circle the carbons in the parent chain. So I'll bring this back to ChemDraw. And I'm going to draw a circle around this. Well, a circle-ish shape is what this is. So that represents the parent chain, these 5 carbons in the parent chain. And then there's a parent chain right here as well. And this divides your compound up into 2 types of carbons. There are carbons that are found in the parent chain and carbons that are branches coming off of the parent chain. And these carbons out here are called substituents. So this is a 5-carbon parent chain with 1 substituent. This is also a 5-carbon parent chain with 1 substituent. So there they're circled. The parent chain is based on the number of carbons in the parent chain. And you need to remember the parent chains that have up to 10 carbons in them. So let's look at that table. If there is 1 carbon, it's called methane. 2 is ethane, etc., all the way down to decane. 11, I believe, is called undecane, and 12 is dodecane, but those are not compounds that I will ask you to memorize. You may see some on the homework that require you to find a great big huge parent chain that goes past 10, but on the exams I'll cap it at 10. There's other things that are more important for you to fill your brain with besides a bunch of carbons and their associated name. You'll also notice that at some point we switched over to Latin prefixes. So pent, hex, hept, oct, non, dec. Those are prefixes that refer to specific numbers. It's the first four that really don't have any numerical designations. Meth is not any language for one that I'm aware of. And one of the common points of confusion that students have is they mix up propane with pentane quite a bit. And so if you just kind of remember that the first four are the ones that the name doesn't give you any indication, doesn't help you with the numbers, and the next five are, hopefully if you remember some of your geometry, you've seen pentagons and hexagons and heptagons, octagons. All right. So you need to remember the name of the parent chains with lengths of up to 10 carbons. What is the name for the parent chain in the molecules above? Well, both of them have 5 carbons, so I left a lot of space for you to type one word, pentane. Now, they're both some form of pentane. Since the parent chain name only specifies the parent chain, we need to describe the branches or substituents coming off of the parent chain. So for this compound right here, pentane describes the parent chain, and there is one branch or substituent coming off of it. And that substituent needs two things. It needs a name, and it needs a locant. So let's deal with a name first. This substituent has one total carbon in it. A one-carbon substituent is called a methyl group. So this is some flavor of methylpentane. The locant is a numerical position of the parent chain that tells us which of the carbons in the parent chain that methyl group is coming off of. And for this compound right here, we're going to start numbering the parent chain from one of these two ends. So it's either numbered 1, 2, 3, 4, 5, or we number it 1, 2, 3, 4, 5. And molecules don't discriminate left from right, so you have to check both possible ways of numbering it. And the correct way to number it is you give it a number system such that any substituents come off with the smallest possible number. So if I call this carbon over here carbon number 1, then my substituent is coming off of the second carbon. If I call this carbon number 1, then my substituent comes off of carbon number 1, 2, 3, carbon number 4. So that means that this is where I'm going to start my numbering, and therefore the methyl group is coming off of the 2 position. And the correct name for this compound is 2-methylpentane. Notice that there's no space right here between the name of the substituent and the name of the parent chain, and the numbers are separated from the letters by hyphens. And this punctuation is incredibly important to an organic chemist. And now we can compare it to the name of this compound over here. This is still a pentane, 1, 2, 3, 4, 5, and is still a methyl group coming off that pentane. So this is a different flavor of methylpentane. And the difference is where the methyl group is coming off. So, and for this compound, it doesn't matter which end you choose to call the number 1 position, because coming from either of the two ends, you're going to reach this methyl group at the third carbon. So this is 2-methylpentane right here, and this is 3-methylpentane right there. We can now answer question 10a. Which name is correct for the following compound? So is it 2-methylpentane or 4-methylpentane? And the answer is this is 2-methylpentane. The molecule does not discriminate left from right, and so while it is the tendency of most languages to number something or proceed from a left to right direction, molecules don't care about that. So we call carbon number 1 whichever carbon of the parent chain allows us to get to a substituent as quickly as possible. So calling this carbon right here carbon number 1 allows us to find the methyl group at the 2 position. So the answer is 2-methylpentane. And the explanation is substituents should be given the lowest number possible. Okay, let's look at a few more compounds and come up with names for these ones. The branched alkane name is given with the locant first, then a hyphen, then the substituent name. So this is just a description of the punctuation system. let's apply this to these compounds right here. So we're going to first find the longest continuous stretch of carbons. 1, 2, 3, 4, 5 is wrong. Again, we have a tendency to work from left to right in a straight line, but molecules don't do that, so we just count till we find the longest chunk of carbons. There's also this 1, 2, 3, 4, 5, 6. And so this is a better parent chain with 6 carbons than this parent chain with 5 carbons. And there's also a 1, 2, 3, 4, and that one's too short, so it doesn't matter. So this is a 1, 2, 3, 4, 5, 6 carbon parent chain. So this is some type of hexane. Coming off of the hexane is a methyl group right there. And the methyl group is coming off of the 1, 2, 3 position of my hexane. If I had tried to call this the number 1 position, then it would be a 4-methyl hexane, 1, 2, 3, 4. And we number the parent chain so that we encounter a substituent at the lowest number possible. So 3-methyl hexane. So the branched alkane name is given with the locate number first. So I put my locate number first, then a hyphen, that's my hyphen, and then the substituent name, methyl, followed by the parent chain name, a hexane with no spaces. So there's the name for that compound right there. Go ahead and pause the video and see if you can name these other 2 compounds. This one we saw before, and it had a common name called isobutane. And that's a correct name, but the name we want is one that follows these rules right here. So pause the video and try to come up with the names for these 2 compounds right here. Well, let's see how you did. I'll just number this. I'll just put the name right here. So the longest continuous chunk of carbons is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6, 7, 8. So this is an octane. Coming off of the octane is a 2-carbon group, so that means it's an ethyl octane. And you could call this the ethyl if you wanted to call this your parent chain. It gives you the same name either way. And the ethyl is coming off of the 1, 2, 3 position of my parent chain. So this is a 3-ethyl octane. Make sure that your punctuation is correct. So it's a number and then a dash and then 2 words with no spaces between them. The last one right here, there are a variety of different ways you can come up with a 3-carbon parent chain. So this is some type of propane. Coming off of the propane is a methyl group, and the methyl group is coming off, if I call this my parent chain, this would be 1, 2, 3. The methyl group is coming off of the 2 position. So isobutane is also called 2-methylpropane. And both of these names, isobutane and 2-methylpropane, are accepted by the International Union of Pure and Applied Chemistry, and that's called IUPAC. So sometimes it'll ask, give the correct IUPAC name for something, and that's just specifying that we're following the right rules. And both of these are accepted by IUPAC. IUPAC accepts all common names, and then it also accepts these what are called systematic names. All right, now time for increasing complexity. What happens when you have multiple substituents coming off of your parent chain? So let's use these examples with their correct names and try to figure out what the rules look like. So this is a heptane. That means that I have a parent chain with 1, 2, 3, 4, 5, 6, 7 carbons. So this is a suitable parent chain. You could also have a parent chain that goes up top. It'd give you the same 7 carbons. But to stay left to right, to keep life simple, I'm just going to call this my parent chain. When I number this the number 1 carbon right here, then I encounter substituents at the 3 and the 5 position. If I call this the number 1 carbon, then I encounter substituents at the 3 and the 5 position. So this is a problem that we haven't encountered before. You can number your parent chain starting from either direction, and you end up with the same pattern of locants, 3, 5. And so now we need to decide which of these 2 substituents is the one that I should give the 3 position and which one is the 5 position. And the answer is only when these numbers are tied, when it's a 3, 5 going one direction or a 3, 5 going the other direction, Then we use alphabetic priority to decide which of the two substituents we want to bump into first. E for ethyl comes before M for methyl, so I want to number it such that I encounter the ethyl group first. So that's why it's a 3-ethyl-5-methyl heptane. For the other compound that we're looking at, there are three substituents, an ethyl, a methyl, and a propyl. And it's an octane, so let's find that parent chain. 1, 2, 3, 4, 5, 6, 7, 8. There's the parent chain. You could also go 1, 2, 3, 4, 5, 6, 7, 8, and this would be a suitable parent chain. It's not, you've noticed this before, we encounter a variety of equivalent parent chains. That's pretty common. But I like this one right here. It's straight across. At the 3 position, if I call this the number 1 position, I encounter the ethyl group, and then at the 4 position, a methyl group, and then at the 5 position, a propyl group. If I number it from the other direction, 1, 2, 3, 4, then I don't encounter my first substituent until the 4th carbon. And so this wasn't an issue where I needed to think about alphabetization. Going from left to right, it was a 3, a 4, and a 5. And going from right to left, it was a 4, and then a 5, and then a 6. And so when you have two different numbering systems like this, you look at the first point of difference. I'm comparing a 3 versus a 4. And it doesn't matter what the rest of the numbers are. The first two numbers are my first point of difference. I choose whichever one is lower. So this could be like a 3 and then a 99 and a 100. And this could be a 4 and a 5 and a 6. And I would still choose the 3 because at the very first point of difference, I choose the lower number, and it doesn't matter what the rest of them are. So for this case, the 3 beats the 4, so I'm going to start from this end, and that becomes a 3-ethyl, 4-methyl, 5-propyl octane. So here is the order of steps that you need to go through when you're trying to name these compounds. First, you identify the parent chain. Then you name the substituents, number the parent chain to give the first substituent the lowest possible locant number, alphabetize the substituents, and write out the name. So we're going to apply that to this more complex example right here, and then I'll pause the video and allow you to work on this other one. If you feel pretty confident, go ahead and pause the video now and come up with your own name for both of these compounds. Okay, let's name this one. I'm going to look first for the parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Looks like it's 10, no matter where I go. So this is going to be a decane. I've identified the parent chain. And now what I want to do is kind of assemble a list of the names of the substituents. So coming off of that decane, I have an ethyl group, a methyl group, and a 1, 2, 3, 4, a butyl group. So it's ethyl, methyl, and butyl. And the order that these are just notes to myself. I'm going to eventually tack these onto the front of the name decane. But for now, these are the three things that I have to worry about. So I've identified the parent chain. I've named the substituents. Now I want to number the parent chain to give the very first substituent that I encounter the lowest possible number. So if I start from this end right here, 1, 2, 3, then the first bump in the road I encounter is at the 3 position. If I number it from this position, 1, 2, 3, 4, 5, then the first encounter I have is at 5, so this end is a higher priority end. I'm going to give this the number 1 position. And notice that I didn't really care what it is that I ran into. The only time I have to worry about which substituent I actually ran into is when I run into the substituents at the same position coming from either end. That was this example right here, where if I start from this end, the first kind of branch I run into is at position number 3. And if I start from this end, then the first branch I run into is position 3. The second branch is 5. Coming the other way, the second branch is 5. So only because the locant pattern was 3, 5 going either direction, then I had to worry about alphabetizing these when picking my numbers. Here it's a 3, 4, 5, 6. It's a 3, 5, 6 coming this way, and coming the other way it's a 1, 2, 3, 4. Whoops, 1, 2, 3, 4, 5, 6, 8. So the 3, 5, 6 is better than the 5, 6, 8. So I don't even worry about what the substituents are. Okay, so if this is the number 3 position, then that means that this is a 3-ethyl. And at the 5 position, I have a methyl group. And at the 6th position, I have a butyl group. So again, these are just notes to myself. I'm just keeping track of what the parent chain is. And notice how the parent chain is the only thing that ends in that A-N-E ending. All other chunks of carbons end in a YL. One of the common mistakes I see students make is they'll have they'll call everything an ethane. It'll be, an ane. It'll be 3 ethane, 5 methane, 6 butane, and decane. And you really only get to use that A-N-E ending one time, and at the very end. All right, let's check where I'm at. I've identified the parent chain, I've named the substituents, and I've numbered the parent chain and given all my substituents their numbers. Now I'm going to alphabetize my substituents. So butyl is alphabetized by the letter B. That's before E, before M. So I'm going to build this thing kind of in reverse. So my methyl group is alphabetically last, so that's going to connect directly to the decane. And then the ethyl group is the next one. Numbers and letters are always separated by dashes. And then the 6-butyl right here is the one that goes out in front. Okay, so that's the correct name for this compound. 6-butyl, 3-ethyl, 5-methyl decane. Let's name the other one. If you want to practice on your own, pause the video, try to come up with your own, and then come back to us and you'll see how you did. Looking for the parent chain, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5, 1, 2, 3, 4. This is some type of pentane. The substituents, so now I want to name the substituents. Coming off of my pentane, I have both a methyl and an ethyl. So I'm just going to kind of write those out in front already in alphabetic order. I'm not done yet. I'm just kind of organizing everything that's at play. If I start numbering it from this position right here, it goes 1, and then I encounter a substituent at the 2, and then the 3. So 2, 3 versus 1, 2, 3, 4. 2, 3 beats 3, 4. So that means that my methyl group right here is coming off of the 2 position, and my ethyl group is coming off of the 3 position. We want to separate letters from numbers with hyphens, and then there's no space between the last name and the parent chain. So this is a 3-ethyl, 2-methyl pentane. If you'll notice in all the previous examples I gave you, all the substituents were different. So it was a butyl, an ethyl, and a methyl. And now we're looking at where the substituents are the same thing. So it's a methyl, and a methyl. Or we have 1 ethyl off this thing and 2 methyls. And when you have that, you lump them together. So this now becomes a trimethylpentane. And you have to have a locant. This is called a locant number. It's the number where that substituent comes off. You have to have a locant number for each of the substituents, even though I've lumped them together. And even if all 3 of the methyl groups are coming off the same position, which isn't possible with the octet rule, but let's consider an example where this methyl group was over here on that carbon. It would be a 2,2,4 trimethylpentane. So you have to specify every single substituent with a number, even if it's the same number for several substituents. Let's just think about this example right here. The decane tells me that my parent chain has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. At the 1, 2, 3 position, I have a methyl group. At the 5 position is my ethyl group. And at the 6 position, I have another methyl group. So the substituents were, I had decane as a parent chain, and then I had a 5-ethyl and a 3,6 dimethyl. And what you'll notice in the order of the name right here is the E is written first, and then you might ask, well, why are the methyl groups later if they start with a D? And they don't. We ignore this numeric prefix when we're alphabetizing these. So I'm not comparing, when I'm trying to alphabetize my substituents, I'm comparing an E with an M, not an E with a D. So that's why the ethyl group still comes out first. So what this did is it gave us a bigger list of things to do when we're naming this. So I gave you a previous one right here where it had 1, 2, 3, 4, 5 steps. And now we had to add in a 6th step where we group the similar substituents and attach the appropriate prefix, di, tri, tetra, penta, hexa, etc. So now let's come up with names for these two compounds using these steps. If you're bold, go ahead and pause the video and try to come up with the names on your own, and then come back and I'll show you how I named these ones. All right, for the A, first I'm going to look for the largest continuous chunk of carbons, and there are a lot to choose from. 1, 2, 3, 4, 5. So there's 5 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is the first time we've seen an example where there are lots of different parent chains, and not all the parent chains are actually the same. If I call this my parent chain, 1, 2, 3, 4, 5, that parent chain has 2 methyl groups here, 2 ethyl groups here, and 2 methyl groups here that are branching off of it. That is 6 total branches. And this is important when you have multiple parent chains that are all the same length. So you only worry about this if all the parent chains have the same number. If they have different numbers, just choose the biggest number. But here, where it's always 5 carbons, then I have to think, well, which of those 5 carbons has the most things coming off of it? So if I start here, go up through this carbon and down here, I end up with 6 substituents. If instead I have 1, 2, 3, 4, 5, notice that this 5 carbon parent chain only has 2 things coming off of it. So given multiple equivalent parent chains of the same length, choose the parent chain that has the most branches coming off of it. So this is my parent chain right here, and this is going to be a pentane. Coming off of the pentane, I have methyl groups. So I have 4 of them, tetramethyl, and I have 2 ethyls, so diethyl. So now I've kind of assembled my pieces. So I've identified the parent chain, I've named the substituents, and I skipped ahead here and grouped similar substituents. So I've already got them in their groups. If it's a tetramethyl, then that means there are 4 of them, and I'm actually going to need 4 numbers out here in front. If it's a diethyl, that means there's 2 of them, so I'm going to need 2 numbers out here in front. And when you number this thing, you actually get the same pattern no matter which direction you go. So if I start from this end, it's 1, and then I have 2 things at the 2 position. So I'll just kind of write those down to keep track of them. So starting from left and working my way to the right, I have a 2, and a 2, and a 3, and a 3, and a 4, and a 4. That is the pattern of branches right there. 2, 2, 3, 3, 4, 4. If I come the other way, then it's the same pattern, 2, 2, 3, 3, 4, 4. So I can pick either one I want in this particular case. All right, now I need to take those 6 numbers and divvy them out across these 2 substituents. The methyl groups are coming off at the 2 and the 2 and the 4 and the 4 position. And the ethyl groups are both coming off at the 3 positions. Okay, so now we need to start putting the pieces together. Alphabetizing this, I am comparing the M, because you ignore any of these numeric prefixes, so I'm alphabetizing it based on the M, and I'm comparing that M with an E right there. So E comes before M, so the name for this compound right here would be 3,3-diethyl 2,2,4,4 tetramethylpentane. Next one. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is another example where there are 2 octanes. This octane right here has a branch right here. That's 1 branch, 2 branches, 3 branches, 4 branches. Whereas this octane up here only has 1, 2, 3 branches coming off of it. So I'm going to choose this left to right octane. So I'll start assembling my name. This is an octane. Coming off of the octane, I have 3 methyl groups. So it's a trimethyl. And I also have a 3-carbon propyl group. And it's not a bad idea. We can go back to this one and look at it. You can actually count the number of carbons in the compound and make sure that your name specifies that same number of carbons. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 total carbons in this compound, so my name should specify 13 carbons as well. Pentane is 5, 4 one-carbon methyl groups is 4, so 5 plus 4 is 9, and then 2 ethyl groups is 2 times 2 is 4, 9 plus 4 is 13. So my name specifies the right number of carbons. Here, 3 methyl groups is 3 carbons. A propyl group is 3 more carbons, so 3 plus 3 is 6, plus my octane, which is 8 carbons, gives me 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I haven't messed up there. And that's kind of a double check you can use if you're paranoid and have an infinite amount of time to take an exam. All right. Now, the Logan pattern. If I start numbering it from this position, then the first branch that I encounter is at the 2 position. And the second branch would be 3, 4. And the third, so this is a 2, 3, 4, 5, 6, 7. So going from left to right, the pattern is 2, 3, 5, 7. Going from right to left, the pattern is at the 2, oops, I did that wrong, 2, 4, 5, 7. Going from left to right, it's a 2, 3, 4, 5, 6, 7. And going from right to left, it's 2, 3, 4. And then a 5, and then another 7. So this is a case where the Logan pattern numbers are exactly the same. So that means that I need to break the tie by alphabetizing these. So the 2, going from left to right, the 2 is an M, and the 4 is an M. M for methyl, sorry. The 2 is a methyl, 4 is a methyl, and the 5 is a propyl, and the 7 is a methyl. Coming from right to left, the 2 is a methyl, and the 4 is a propyl. And there's my first point of difference. So I am comparing a 4 that is a methyl with a 4 that is a propyl. Alphabetically, M comes before P. So I'm going to number this thing from left to right. So this is my Logan pattern right there. One time I mentioned as a joke that students should ask the testing center when they tell you what you can use. I said you can use an alphabet strip on that. And the students in the class understood it was a joke. One of the students went to the testing center and they asked him what he could use, and he said he could use an alphabet strip as a joke, only the person in the testing center didn't get the joke. So they had to call their supervisor and ask where the alphabet strips are. And it was one of those things where the joke got to the point where the student who asked for the alphabet strip no longer felt comfortable telling the person that it was a joke, so they just had to write it out. And I got a phone call asking me why I specified alphabet strips, and then it was funny. Kind of a weird conversation to have on the telephone. Okay, so the methyl groups right here are coming off of the 2 and the 4 and the 7 position. Oh, whoops. And the propyl group is coming off of the 5 position. So I've got all the pieces now. I'm ready to alphabetize the substituents without using the prefix. So I am comparing an M with a P. And this is a case where if you forgot to ignore the prefix and you used it, you would be comparing a P with a T and would get the wrong answer. So M comes before P, so coincidentally these happen to already be in the right order. So there's my name, and I'm done. Okay, in the summary, if the other lists that I gave you were not enough, here is one more list with a little bit more description. And so you should be able to use kind of the summary list to name these last 2 compounds right here. I have a handful of textbook problems for you, and then you can go ahead and upload your assignment, and you're done. Let me help you answer these ones. Again, I would encourage you to pause the video and try to answer them on your own, and then come back when you're ready to see what the correct answer is. So pause now. Okay, welcome back, or you just kept watching. So let's first pick our parent chain name. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 versus 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. Yeah, it's 9. So this is some type of nonane. And I need to pick, when you're given 2 parent chains of equal length, we pick the one that has the most substituents coming off of it. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This route right here gives me a methyl group and an ethyl group coming off of it. Some of you that loved organic chemistry enough that you've already taken it might ask, why don't I just call this an isopropyl group? And the short answer is that if you try to number this, call this your nonane and say I have an isopropyl group coming off of it, that's only one substituent. And we're trying to choose the parent chain that has the most substituents. So this is my nonane. I have a methyl group coming off of the 2 position and an ethyl group coming off of the 3 position. Ethyl comes before methyl alphabetically, so it's a 3-ethyl 2-methyl nonane. Let's check the rule system. First, I determine the parent chain. I look for the longest string of carbons, and I found 2 different parent chains of 9 carbons. If you find 2 or more parent chains of identical length, choose the parent chain with the most substituents. And that's how I was able to choose this as my parent chain and not this as my parent chain. Name the substituents. So I put the nonane down, and then I have an ethyl and a methyl. Number the parent chain, number in such a way that the first substituent is given the smallest number. And then I write the name, group any similar substituents with diatribe tetra, alphabetize the substituents, use hyphens to separate locants from substituent names. These numbers are called locants, so I've used hyphens to separate those. And then if I have a string of similar numbers together, then I use commas to separate those. So I didn't even need all the rules to name this one right here. Let's look now at letter B. Let's find the parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That looks like that's going to be my parent chain right there. This one's going to get messy, so I'm going to pull it over in a ChemDraw to pull this thing apart. And so this right here is my parent chain coming down this line. So I'm going to go ahead and just label that parent chain with carbons so that you can kind of see where that parent chain is. And it doesn't matter which of these 2 I choose. Okay, so if the parent chain is the one labeled with these carbons right here, then we count the number of substituents, and there's 1, 2, 3, 4, 5, 6. There's 6 total substituents coming off of this parent chain. And you're not going to find another parent chain with more than 6 substituents. So this is my parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is some type of nonane right here. Coming off of the nonane as a parent chain, I have this over here is a methyl group. And then I have an ethyl group and a propyl. And let's go ahead and just kind of tack those where they go. This is my methyl group right there. Here's my ethyl group. There's my propyl group with 1, 2, 3 carbons on it. I got a couple more methyl groups down here. And then I have another ethyl group over here. Okay, so 1, 2, 3, 4, 5, 6. I've got my 6 labels for all of my substituents. And so now I'm going to take these, and I got to come up with a numbering pattern for this. So if I call this carbon right here carbon number 1, then the pattern that I get as I try to go down that parent chain is a 2 and a 2. There's 2 different things coming off of that second carbon. And that is, I'm going to stop that. I can put the rest of the numbers in, but I don't need to, because if I start at the other end, then the first substituent that I encounter is still at number 2 carbon, but the second substituent I encounter is at the number 4 position. So it really doesn't matter what any of the rest of the numbers are until I have to name it, so I may as well come up with them. So I have an ethyl group at the 3 position. I have a propyl group at the 4 position. 5, another ethyl group at the 6 position. 7, 8, and a methyl group at the 8 position. And then for this one, it's going to be 2, and then 4, 5. I have 6, and then 7, and then 8, and 8. Okay, so there is my full list. And all I really do is compare those 2 lists and work my way from left to right until I encounter the first point of difference. And the first point of difference is a 2 versus a 4. Since that 2 beats that 4 on bottom at the second position, I don't have to make any other comparisons, and this list that I just put together is worthless to me. So there's my Logan pattern, 2, 2, 3, 4, 6, 8. So now we're ready to kind of put all the pieces together. I've got methyl groups. So I have 3 methyl groups, I have 2 ethyl groups, and I have 1 propyl group. The propyl group is coming off of the 1, 2, 3, 4 position. So this is a 4-propyl. My methyls, because there's 3 of them, that means it's a trimethyl, and they are coming off of the 2, and the 8 position. And then I have 2 ethyl groups. One of them is coming off of the 3 position, and one of them is coming off of the 6 position. So that would be 3,6 diethyl. Okay, so I have 1 substituent plus 3 substituents gives me 4 plus 2 substituents. I've still accounted for my 6 substituents, and I've taken those numbers and just kind of redistributed them where they belong. Okay, now we need to alphabetize these. The diethyl is alphabetized by the letter E, the trimethyl is alphabetized by the letter M, and the propyl is alphabetized by the letter P. So the name of this should go 3,6 diethyl dash 2, 2, 2, 8. Notice how all the numbers are separated by commas and from each other and separated from letters by hyphens, noname. There's the full name of this. Sometimes students will start their answer at the end of a piece of paper, and then they'll have to kind of do this deal where it breaks right there. And then because it might be in your best interest to tell me that you know that there's not a space right there. So sometimes I'll see students write little notes like this and then put an arrow to specify that they know that there shouldn't be a space, but they ran out of paper. And so it looks more like this because why would you do this if you had room to write no space? You'd be out of paper. So they do something like this to show me that they know that it shouldn't have a space or anything like that. They just needed to break it off down to the bottom. ChemDraw has an auto naming feature. Control-Shift-N, which I always forget the command streaks for. Control-Alt-N. And so the name that ChemDraw came up for this was, let's see how we did. 3,6 diethyl 2,2,8. Yep. So ChemDraw got it right, is what I'm going to say. So I'm going to take this name now and just copy it back over to my original document and drop it in. So there's the name.